Hey everyone. All right, so last night we got everything hooked up, and the thermal camera is working. So what we're gonna do now, I'm gonna hook up another camera so you can see what the thermal camera finally looked like, and we're gonna turn it on, and I'm gonna show you how it's all working. So give me a second here to juggle some things. Get it all ready to plug in. Alright, so I'm plugging in another camera here so we can take a look at what it looks like. And here we go. Let's see if I can get this camera turned on. So this should be... There we go. Alright, so we have a little camera here. Makes it a little bigger. Let's just, for the sake of it, I was going to try and split screen it, but this is not working the way I wanted. Anyway, so here is our final setup here. Looks like we're having some exposure issues. Let me see if I can deal with this. Alright, so what you're seeing now, I'm trying to show you our overhead camera setup and the thermal camera. So give me 1 second. So what I need to do is manually set my exposure control on this camera so we can actually see what's going on here. Okay. So, almost there. Okay, so what you're looking at here is we have the camera that is our overhead camera. So that's this camera. And then we have our thermal sensor is this camera. And what we're going to do is I'm going to turn on, let's just put this down here, face it up so you can see what it's seeing. Not doing really well with this like second camera management thing here. Okay, let's shrink this down. Okay, we're gonna put this bump. There we go. That is more manageable. If you're just tuning in, what we're doing is we are going to review what we did for our thermal camera and show it working. So yesterday we were hooking up a thermal camera and I mounted it next to our camera. So if you're looking up from this camera, let's see if I can point, we have that is the camera, and then next to it is the thermal camera. Let's try this so we can point. Okay. Okay, so the thing that tweezers are facing on the camera, thermal, and that's regular. All right. I'm going to stop chatting and we're just going to turn it on to see what it looks like. Alright, so I'm starting up my application that I wrote, and we are starting to get our thermal overlay going. Alright, look at that. Okay, so this thing is refreshing, I think, slower than it's supposed to. It feels like this is not going at 10 frames a second, but it is going at 1 frame a second. So that's, I think I'm going to look at my code next. But right now what you're seeing is I have set an overlay in OBS so that wherever the heat is, it shows that on this mat that's overlaying it. So let me turn that down a little bit. So let's thermal overlay, filters. I'm going to change the opacity to 50. Actually, I'm going to turn it down even more. So let's set the opacity to 20. And I'm going to move the smoothness up here so we have a little more of a... Okay. Okay, so now wherever there is heat in my environment, it's trying to follow it. So yeah, what this is just gonna give me a desktop monitor so I can keep track of what is hot on my desktop. And what you're seeing in this bottom corner near where my hand is, I'm heating up the table so it stays warm there past when my hand leaves. And it's got a lot of noise, but numerically this data works pretty well. It's only an 8 pixel by 8 pixel thermal sensor, so that's only giving us 64 active pixels. And the field of view of our thermal imager is actually wider than the field of view of our camera, so we have to zoom it in a little bit. So we're really only getting like 5 pixels by 5 pixel resolution for our desktop monitor. All right, so the next thing we're going to do is we are going to figure out where first I'm going to turn off this camera, because we don't need that camera working. Just going to take it and reset it back up. We use this to monitor our oscilloscope when we are doing a project with the oscilloscope. So put that back to where it lives. Okay, and we can move that stuff out of the way. And next thing we're going to do is I'm going to bring up our code, and we're going to try and figure out why this thing is only running at 1 frame per second. So I'm going to stop it. Okay. And let me find my window capture that is showing our software, or at least our Python. Okay. Nope, that's not it. Aha, okay. So there is our Python code. Okay, so what we're going to do is first we are going to dive into this code and figure out what is going on. So why is it running so slow? And I have a feeling it probably has to do with our sensor code. So I'm going to dive in here and we're gonna go on to Google, because Google is our friend, and we're going to see if there's any settings in this adafruit library that make this thing run faster. Actually, and what we're going to do before we do that is we're just going to go into it. So we're using PyCharm, and in PyCharm there is a nice little method you can use called implementations, which is Control-Alt-B. That takes us right into our library. So I like this repo. We're going to take a look at that. We're going to open that up in Google. So let me also enable our browser window over here so we can see what the browser is doing. Need to clean up my layers a little bit. So give me 1 second. I'm going to clean up my layers in OBS so I know what is going on. Okay, we're going to call this browser. Give me 1 second. I'm renaming. Nope, that's not browser. That is our Python IDE. And we have room mic. And what is this text? Okay, we don't need that text. We kill that. We have our Wi-Fi cam, and we're going to rename that to drill and belt saw cam. Okay, we have a screen capture, which we're not using. We have oscilloscope head cam. We're not using any of the head cam information. So what I'm doing, I'm sorry, this is boring at the moment. I'm just cleaning up my inputs in OBS so that we have, the most efficient stuff here. I have a workbench, okay. Okay, now I have my layers put up properly. So what I'm going to do is I'm going to open up, let me lock that, and lock that, and lock that. Okay, so I'm locking a few of these things. Okay, so those are all locked. Now what I'm going to do, we're going to call this title. Yeah, this is our title info. Let me rename that. Okay, so now what we need to add is we need to add a window capture, and the window capture is going to be our browser. Okay, so browser, and I'm gonna click the browser, which is Adafruit. Okay. Okay. So here we go. And we don't need to see URL, so we're gonna put the browser down a layer or two. Okay. All right. So now we have our information here for this library. Let's see if it's got any usable information in here. Make sure to solder the jumper. Okay, that's if we're doing that. Pixels read with that. Information. Okay, let's go here. Well, this doesn't look like it's going to be much help. Okay, so we're going to go back and let's take a look at examples. So this is setting different min and max temp. That's interesting. So that's setting the bus. Let the sensor initialize. Then it reads the pixels. And it draws and it updates. And there is nothing in here that is setting the refresh rate. Okay, so let's go back. Let's see if this one has anything about refresh rate. Board sensor, range, colors, or mapping the colors, print their value. Nope, nothing there. Let's see the simple test. Help us out. Doesn't. Okay, but what we're going to do, I want to see where our bottleneck actually is. So we are going to, first we're going to, well, we have this one. This is our original code here. So let's take our original code and we're going to just run a test on this. So it should be AMG pixels. Okay, so let's home. And what we're going to do is we're going to just basically build ourselves a timer here. And we actually have two things. So we have pixels and we also have temperature. Okay, so if I run this code, this is what we built a few days ago. This should just be polling these things. So print and that and okay, so this should print these two things. So let me just do this. I'm gonna just run this, and this should just print out our temperature of the board. It does it once, so we're gonna put this in a loop. So let's do while true. While true, do this. Well, that's running nice and fast. Ooh. Okay, so that's running fast. Let's see what happens if we try this one instead, see if it runs just as fast. And then if it does, we're going to figure out where our bottleneck is. Okay, that's not running as fast. So let's see what our let's build ourselves a little timer here. So time dot let's see how to do this. Let's just Google it. Let's just do Python time FPS. love how you can just find what you're looking for online really easily. You just gotta know exactly how to search for it. Makes coding a lot easier. So what we're gonna do here, so what this is doing is it's starting a timer. It's creating start time with time.time, and then it's running our code, and it's printing out the next line. Our frames per second is 1 frame over whatever time is now my start time, so that gives us our process time. So we're gonna run this. 0.88. Okay, and then if we run this with temperature, let's see what this gives us. That's saying it's 30 frames a second. Okay, so my question now is, what is the actual refresh rate of this board? So we are going to do AMG 88XX rate ball pixels. Okay. So this is saying a bunch of info about this thing. Real-time heat mapping, rear body radiation, and the Stefan Boltzmann law. We're reading all this stuff. We don't need to read all the science behind this. We've done that before. Part description. Okay, here is where it gets interesting. So it says right here, 10 hertz data rate. I2C for fast acquisition, which is how we have it hooked up. So the AMG 8833 also uses I2C communication with the Pi. Okay, not with the Pi, that's not what we're using, but we are using something that is fine. So the data transfer rate is quick as well, so there is no concern of lag between component performance and reading data into Pi. Okay, so the features along performance, therefore, okay, due to issues I will discuss below, the update rate is closer to 1.6 seconds because the graphics requirement from the Python plotting tool, however, is only due to limitations of the Pi, not the sensor. If you want to read a full, okay, so it's saying that that is due to the Raspberry Pi. We don't have this hooked up to a Raspberry Pi. We have this hooked up to a full-fledged computer. So let's see where our lag is coming from. All right, so that's something that has to do with the printout. So what we're going to do is we are just going to call this and see what happens. If we're going to comment that out, we're going to just call the values and see what happens. Because I'm curious here. So that says it is less than 1 frame a second. Alright, so that doesn't make any sense. So what we're going to do is let's check the let's check our I2C. Let's check this board and see if we can change the frequency on the board, because maybe that is it. So let's type in this board. This board is the FS232H. I believe it's FS232H. I should have written that in the description. Adafruit. This thing might help us. FT232H. And let's type in I2C frequency. Okay. So let's try and figure out if this might be our controller board is having an issue resolving the data. That was no help. If anybody who's watching this has any ideas, that'd be great, but yeah. What it seems like is something is not working with this. Like, our frames per second output here is only, it's less than 1, and theoretically this sensor should be doing 10. Okay, so this says busio. Let's see. How do I set bus IO speed? Okay, so it's saying here that if you're using, so let's look at this Blinka. It says that, so using this board, so keep in mind basic limitations. SPI and I2C cannot be used at the same time since they are sharing some same pins. Already understood. GPIO speed is not super fast, so try and do any arbitrary bit bang like thing may run into speed issues. there's no analog to digital converters, no digital to analog converters, and the UART is not available. It's a different FTDI mode. Okay, but that doesn't say anything about our I2C port being slow. So let's see what this says. If there's anything here about checking the speed of our I2C port. So Linux, yada yada. Did all this stuff the other day. Set the port post install check. We did all this stuff. Use ether when I2C mode on, not use. Okay. Okay, so let's see. The new version has a switch that connects D1 and D2 for easy I2C interface. Move the switch on. Original version, 2 pins must be tied together. Okay. Here, we got I2C example here. It's all wired up. Let's see if they set the I2C board speed or the interface speed. So this is create library object using bus.io or bus I2C port. That's that. It's got nothing about setting a frequency for that. We're in SPI now, so we don't need SPI. Let's go to fact and troubleshooting. Board not found, no. Mixed SPI, no. No pull up, no. So in this, for Raspberry Pi, it says that the I2C bus speed is 10 kilohertz to fix it. I don't know what that means exactly, because I don't know how to set it on this. So let's see. Let's try this. Let's try. Are specifying on M0. So we can set frequency. Maybe. and that's in our bus IO library. So let's setting it to 100,000. Let's see what happens if we set this to 10K. Okay, so we're going to close that. Okay, back here. Okay, let's try this. Ah, so that lowered it. So let's turn it up. Pack it up, pack it in, let me begin. We are hacking it, and it is not a sin. Okay. I'm just plugging in numbers here, so let's see if I don't fuck it up. Alright, so let's actually, before we start putting in random numbers, let's check this thing out. Let's do, it is the FT232 HI2C clock speed. Okay, hardware description. So, the MPSSE always generates the clock. As such, is always the I2C master. It is not designed for multi-master. Okay, so let's see where this lives in here. So in this, we're gonna just look for this. Okay, so I2C, and we want to see our clock. Clock stretching. Okay, it does not support clock stretching. Has an adaptive clock feature. One solution may be to reduce the SCL rate. Some peripherals do not use their clock stretching capability at the lower I2C clock rates. So what is the internal clock of this thing? Clock frequency, two-phase clocking is 153.8 kilohertz. That's 100 kilohertz, three-phase clocking, 400 kilohertz. So let's just type in kilohertz here. That seems like clock divider set. 600 kilohertz is used as the basis due to the actual rate being a third lower than the three-phase clock mode. Okay, so that doesn't like that. Let's trace this back. Let's put it back to 4. Okay, let's try 5. We're just arbitrarily popping in numbers now. Did something. Saying we're reading back at still 1 frame a second. But I would bet you if we read our temperature, we're going to get faster. So let's just duplicate that. We're going to kill that. We're going to actually kill that. We're not actually going to print it out. So let's not print it out, but let's actually see what it spits out. Yeah, we're getting 30 frames a second there with our temperature read of the board. I wonder if we lower this down to 10K, if that slows that down. It does. It slows that down to 24 frames. And if we slow it down even more, what happens? That's 1,000. I should give it to 10. Okay, that's 10. And let's see if that clock slowing down. This is inverse to what I would be thinking, but if I slow down the clock, maybe more data can come through. Nope. That did not do it. So I'm starting to think that our bottleneck is actually our I2C on this board, which is disappointing because I was looking forward to this being a nice fast board, but I guess it's not. Why? What's the fastest we can give this thing? Did we give it a megahertz? No, give it 600 kilohertz. Nope. We hit 5. What happens if we add a 5 in here? Does it? Nope. So 5,000, 5 kilohertz. 5,000 kilohertz is the highest it looks like this goes. Ooh. Maybe not. Let's put in some random numbers here. Slowly just creeping up. 5. It doesn't like that. Do 9 there. Nope, that's too high. Put 5. 6 works. Let's see if 6 works. 6 works. What about 7? Nope. 5, 6. Alright, so let's try it again with the pixels. See what happens. Yeah. Alright, so let's see if anybody has also stumbled upon this bottleneck. So this is, what is this chip again? Alright, so what's this little dip switch for I2C mode on and off? Okay, so we now have a modern USB-C connection on the board instead of the micro USB. I2C switch to connect D1 and D2 for easy I2C interfacing. 3-volt output, let you plug in okay, well that doesn't turn it on off, it just connects those two things together. Can be set between, so the clock on D0 can be configured at run speeds between 450 Hertz and 30 megahertz. Okay, so let's try this instead. Okay. So what we're actually going to do is we're gonna copy this file because I don't want to fuck up everything that's in here. Okay, so let's steal this line. And take that line. Disable this. I'm going to take this. I don't think this is going to work, but we're going to see what happens if I just run this. Yeah. Okay, that didn't work, but it needs a sudo, so maybe it will work. I'm going to try it as sudo. Make sure the driver is not in use. I'm able to claim the driver. So what we're going to do is we're going to unplug it for a second. We're going to plug it back in. Try it again. All right, so it says that we can't set it from the... Okay, so let's just kill that. Right. So line 20, it's that line. Can't find... Okay, so what is pissed off about this now? Takes two, write data takes 2 positions, 3 arguments were given. What line is this? So line 9 is giving us an issue. Let's turn this off. Just curious what happens. Right, that's of course gonna error. See if the internet has a solve for this. Like we've been here before. It's a library issue. Okay. So we're going to go back through installing the libraries for this thing. It seems like that might be the problem. pip3 install pyftdi. Alright, so that's already installed. Okay, that's already installed. We have our udev rules already installed. Let's just check them. Why not? So sudo nano /etc udev rules 11. Yep, those are all there. Okay, so pip install fpy. I think we already just did that. We did. Let's install adafruit blinka, which I think we already have. Adafruit blinka is already installed. We set the environment variable. Post install check. We've done this. It's in our code. We did these things. So why is this code not running? Hello there, how are you? Professional grade. Professional grade beginner, how's it going, man? You have any words of wisdom for how to solve this problem? Yeah, run my sanity check here. Avoid mixing libftd I 1.2 with Python 3. Either use 2.1 and Python 2 or 1.4 and Python 3. What version of libftdi are we using? That's a question. Oh, no, that's version 1.4. Let's try this thing. Alright, so what did that do? Did that do anything? Is that gonna fix? Nope. so we're going to try this. Let's just do this. Just do pip 3 install adafruit GPIO. So that means that I should be able to run Python. So I should be able to just execute this without this line at the top. And it's doing something different. I'm not sure what it's doing now, but it's doing something different. So we're going to cancel that. And what we're going to do is we are going to run adafruit fix. Okay, well actually, we're going to also kill this line. We're going to try it again. Okay. Okay, so let's just add these to our global repository. Let's see what happens if we just pip 3 install adafruit GPIO. This thing is just pissed. We're going to revert back to Python 2 for a few minutes, see what happens if we just use Python. Okay, so that's fine. Line 9, there is no import adafruit XX. Why? So it really is this code about the FTDI serial driver. Well, yeah, let's just fucking edit it. What happens? Oh, look at that. Well, that worked. Alright, so we're making progress here. Must be called with adafruit instance as first argument, got nothing instead. Whoa. Okay, well that did something. We're getting 1 frame a second. Alright, so that did something. Let's change this back to 70. That's not going to do anything. Okay, so let's get rid of this. What are our other options here? So we have AMG dot Well, that's all I got right now. I'm going to sign off and see if I can fix this later. Thanks for tuning in.